Hello students. In this video, we're going to explore the intriguing concept of the magnetic effects of electric current. When we talk about the magnetic effects of electric current, we're referring to the ability of an electric current to generate a magnetic field around it. This concept was first discovered by Hans Christian Ørsted in 1820, who observed that a compass needle was deflected when placed near a current-carrying wire, revealing the close relationship between electricity and magnetism. This discovery paved the way for the development of electromagnetism, which is crucial for the functioning of electric motors, generators, and transformers. Let's begin by revising magnetism. A magnet's field is strongest at these poles, and it's important to note that like poles repel each other, while opposite poles attract. This fundamental principle is mirrored in the magnetic fields generated by electric currents. A magnetic field is the area around a magnet or a current-carrying conductor where magnetic forces can be detected. You can think of it as the force field that extends around a magnet or wire, influencing other magnetic materials or currents within its reach. Magnetic fields can originate from two primary sources: permanent magnets and electric currents. While permanent magnets have a fixed magnetic field, electric currents generate a magnetic field only when the current is flowing. To visualize this concept, imagine a current-carrying conductor, like a straight wire. When electric current flows through this wire, it creates a magnetic field around it. The magnetic field lines form concentric circles around the wire, with the direction of the field depending on the direction of the current. This is where Maxwell's right-hand thumb rule comes in handy. If you grip the wire with your right hand, with your thumb pointing in the direction of the current, your fingers will curl in the direction of the magnetic field lines. Now, what happens if we shape that wire into a loop? The magnetic field lines produced by the current will become denser at the center of the loop, and if you add more loops, creating a coil, the magnetic field will strengthen. This structure, when current flows through it, is known as a solenoid. A solenoid generates a magnetic field similar to that of a bar magnet, with distinct north and south poles. The strength of this magnetic field depends on factors like the number of turns in the coil, the current passing through it, and whether a material like soft iron is used as the core. This brings us to a critical application of this principle: the electromagnet. An electromagnet is essentially a solenoid with a soft iron core, and it becomes magnetized when current flows through the coil. The beauty of electromagnets lies in their controllability. You can adjust their strength by varying the current or the number of turns in the coil, and you can even turn them off by simply cutting off the current. This feature makes electromagnets incredibly useful in a variety of applications, from electric bells to cranes used for lifting heavy magnetic materials. Next, we must understand the force on a current-carrying conductor in a magnetic field. When a conductor with current flowing through it is placed in an external magnetic field, it experiences a force. This force is perpendicular to both the direction of the current and the direction of the magnetic field, and its magnitude depends on factors like the strength of the magnetic field, the current, and the length of the conductor. This principle is the basis for electric motors. An electric motor converts electrical energy into mechanical energy. It consists of a coil of wire placed within a magnetic field. When current flows through the coil, it experiences a force that causes it to rotate, producing motion. This rotational motion is harnessed to perform work, such as turning the blades of a fan or driving the wheels of an electric car. In addition to electric motors, another significant phenomenon related to the magnetic effects of current is electromagnetic induction. This is the process of generating an electric current by changing the magnetic field around a conductor. Discovered by Michael Faraday, electromagnetic induction is the operating principle behind electric generators. A generator converts mechanical energy into electrical energy by rotating a coil within a magnetic field, inducing a current that can then be used to power electrical devices. When we talk about electric currents, it's important to distinguish between direct current, DC, and alternating current, AC. DC is a current that flows in one direction, while AC periodically reverses direction. Most household electrical systems use AC because it is more efficient for transmitting electricity over long distances. Finally, in our homes, domestic electric circuits are designed to safely distribute electrical power to various devices. These circuits often include safety features like fuses and circuit breakers to prevent damage from short circuits or overloads, which can cause excessive current to flow, leading to fires or equipment damage. Now, here's a question for you to test your knowledge. What rule would you use to determine the direction of the force on a current-carrying conductor in a magnetic field? Please share your answer in the comments. The complete curriculum for Class 10 is available on our channel. Check out all the links provided in the description below. Please make sure to like, share, and comment for more such videos.